Please welcome the Deputy Director of DARPA, Dr. Peter Highnam.
In this session, we're going to talk about something that DARPA is doing called the DARPA Risers. I'm going to explain what this is about and introduce you to three of the risers we've selected from the class of 18 to represent and to show you the value and the quality that we have. So DARPA works at the intersection of national security and science and technology. Our job is to avoid and to impose technological surprise, and we focus on the hardest problems. As you've seen from this meeting, we have 60 years now of amazing accomplishments. Now, when you look inside the box about how things get done, it's people. So inside the organization, the most interesting job, I think, in the government is to be a DARPA program manager. It's the most fun, where you can make a huge impact and really get things done. But you're here for a short period of time. You come in a hurry, you push, you make it happen. The other type of people who really make things happen are all our partners, and that's many of you. People in the universities, the companies large and small, the national labs, the FRDCs, the UARCs, the services, the service labs. That's where the bulk of the work gets done. That's where the research gets done. That's where the unsung heroes are in those organizations, not just the principal investigators, but the people actually doing the work at the lab bench, the test range. These are really important people. And to make all this work, to make DARPA continue to deliver into the future, we have to ensure a continuous flow of passionate, talented people, both within those organizations, working in our research programs, but also, of course, coming on board as PMs. So with the DARPA Riser program, first run in 2015, DARPA seeks to find, recognize, and encourage people to pursue careers at that same intersection, science and technology and national defense, a career of service, to be part of something bigger than oneself, our nation's security. So DARPA Risers are early career scientists, technologists, and engineers. Again, the unsung heroes of today, they're buried in the mix. They're the postdocs, the grad students, the engineers that are working at the bench. So what we've done is we went to the program managers in-house at the moment and said, who do you recommend? Who would you characterize as somebody you want to encourage, to mentor, to be part of DARPA's future, to ensure we keep delivering? So what we ran this drill, and you'll see some examples here of poster sessions and presentations, and it worked. And we now picked three risers to come on board, to come up here today to present examples, again, of the quality and depth of these people. In 2015, we had about 54 risers. Some of these people are now leading research as principal investigators, and yes, wearing the parochial DARPA hat. One of them is now a program manager already. So Dr. Jeff Haas has joined and is in the Strategic Technology Office. In 2018, we have 47 risers, and I'd like to ask the risers please to rise. If you would, please stand up. Please give them a round of applause. I think you'll agree from the three examples that we're going to show you today that they're already doing amazing work. Amazing today, they'll be amazing tomorrow, and yes, I really hope they'll become program managers at some point in the future too. Thank you.
Ladies and gentlemen, please welcome our first DARPA Riser presenter, Jelena, Notaros.
So thank you for that lovely introduction. As mentioned, my name is Jelena Notaros. I'm a graduate student at MIT. Today I'll be introducing you to the Visible Integrated Photonics Enhanced Reality System, or VIPRE for short, which our group at MIT is developing. VIPRE is an integrated photonics-based head-mounted display that will enable the next generation of augmented reality technology. In general, a head-mounted display is an optical system that displays information directly in the user's field of view. These systems enable the user to remain engaged with their surroundings while referencing information directly to real-world objects and events for an immersive augmented reality experience. Due to these advantages, head-mounted displays have seen use in a number of areas, including in the military, medicine, engineering, and gaming. In a typical head-mounted display, a microdisplay that sits on the side of the user's head is used to generate the desired image. An optical relay system then takes that image, magnifies it, and projects it onto the external scene in the user's field of view. However, these current systems are bulky, heavy, and relatively dim, which makes them highly indiscreet and inadequate for use in normal daylight conditions. Additionally, these systems project images at a single virtual focal plane, whereas in the real world, objects naturally lie at multiple focal planes. This inconsistency results in the divergence accommodation conflict, which fatigues the user's eyes and limits long-term usage of these displays. To address these limitations, we've developed the VIPRE integrated photonics-based head-mounted display that sits directly in front of the user's eyes. This direct view near-eye modality enables the display to project holograms with appropriate depth cues to resolve the divergence accommodation conflict and enable long-term use. Additionally, these displays utilize transparent chip-based fabrication technology to enable a completely flat and highly discrete solution to head-mounted displays. The VIPRE system leverages the rapidly advancing field of integrated silicon photonics. In silicon photonics, we take standard CMOS fabrication processes, but instead of forming transistors and manipulating electrical signals on computer chips, we form these CMOS layers so they actually confine, guide, and manipulate light on chips. And by using this low-cost, high-volume wafer fabrication technology, we can now create optical systems that were once complex and bulky and expensive, and we can integrate them onto photonic chips that are relatively cheap to make and that have very small form factors. For example, we can create advanced optical systems that monolithically integrate photonics with driving electronics on a single chip, as we did in the DARPA POEM program. Similarly, we can monolithically integrate lasers, the optical light source, onto these chips, as we showed in the DARPA EFI and DOTOS programs. Now, one of the promising systems that has come out of all these programs is the integrated optical phased array. The optical phased array concept borrows heavily from its radio frequency or RF counterpart. The general idea is that we have an array of antennas, and by individually controlling the amplitude and phase of the light that's emitted by each of these antennas, we can dynamically control the light that's emitted by the array itself. And now, when we take this optical phased array concept and we integrate it onto photonic chips, and we leverage the deeply scaling power of integrated silicon photonics, we can now demonstrate optical phased arrays with greater than 10,000 antennas on a single, flat, millimeter scale chip. Using this technology, our group has already shown a number of promising demonstrations, including far-field beam steering and high-fidelity pattern generation. We have then taken these optical phased array systems and applied them to a number of emerging fields, including light detection and ranging for autonomous vehicles and high-speed optical data communications. For the VIPRE system, we're taking this optical phased array concept and applying it to the visible light regime to create a visible light pixel that's tuned using novel liquid crystal technology. We will then take approximately 1,000 of these phased array pixels and integrate them onto a grid, a two-dimensional grid, to create the full VIPRE display. Finally, we will use a transparent electronics driving backplane to encode the light that's emitted by the display such that a hologram is generated for the user to see. As a proof of concept example, we've recently shown a passive demonstration of this type of system, and you can see here high fidelity between the simulated and the experimentally measured far-field image. In conclusion, using novel and mature silicon photonics technology, we have developed the VIPRE system to enable a compact and efficient head-mounted display for daytime operation and long-term discrete use. With that, I'll wrap up. I want to thank you all for your time. I'd like to thank my group members and advisor. Without them, all this work wouldn't be possible. And I'd finally like to thank the organizers and the DARPA leadership for the incredible honor to be speaking to you today. Thank you.
Ladies and gentlemen, please welcome our next DARPA Riser presenter, Stephon Lee.
Hi folks, I'm Stephon Lee, and I'm excited about the promise of training embodied agents in perceptually and semantically rich simulation. So when I say embodied agents, what I mean is agents that can perceive their environments, can communicate about this understanding with humans in order to coordinate their actions towards mutual goals. So obviously this incorporates quite a few AI fields, including machine perception, natural language processing, and reasoning and control, or planning and control. And I don't think I have to argue too hard to this crowd that where such agents would have the biggest impact is if they were in the physical world, right? We want our robotic butlers, we want our robotic warfighters. But I'm going to put forward the argument that maybe we don't have to start there when we're training them. So the real world has a number of challenges for training these kind of agents. For instance, it's slow. Life moves fast, they say, but not on the scale of training agents. They can run at most at real time. And you can parallelize them, but there's a linear scaling cost. And perhaps more problematic, it's difficult to benchmark results between systems and platforms and even across individual experiments. You can't recreate the initial conditions of reality. You can't go back in time. So it's hard to tell if algorithms have improved. And finally, it's expensive. From the agents themselves to the environments you have to construct for them to navigate through, and the mistakes they're going to inevitably make early in training, physical robotics is expensive. And the argument I'm putting forth is that many of the skills that we'd want these agents to have could be acquired first in simulation. And specifically, I mean perceptual skills, linguistic skills, and reasoning skills. I'm not making an argument towards control. So what do we need in order to get agents to learn these specific skills? Well, we need a simulator of some kind, environment of some kind, large scale, diverse settings, full 3D. And it has to be semantically and perceptually realistic. So perceptual realism, things look like they should. And then semantic realism, the environments are laid out in a way that makes sense. Cars are in garages, bathrooms seldom have exterior doors. These sort of things that we use every day as regularizers when we interact with our world. Common sense. We also need a simulator built on top of this that allows the agent to move around these environments, something that emulates just basic physics should do, because we're not targeting control in this case. But it should be fast and easy to query this perception. We want to run millions of iterations of simulation in a short time span. And finally, and I think maybe the trickiest bit, right, the graphics community has done a great deal of work on the first two, but we have to think of tasks. Right? We need to think of things we can make these agents do in these environments where they're forced to learn the skills that I sort of promised earlier. And the good news is in the last year, there's been a tremendous amount of work on these topics in the machine learning and computer vision communities. And we'll touch on some of those later. But I want to start by sort of examining this environment simulator task vertical stack from some of our recent work in our lab. So I want to talk about the embodied question answering task. So in this task, an agent is spawned at a random location in a never-before-seen environment and asked a question. What color is the car? The agent then has to navigate through this environment using first-person vision alone, having never seen the environment and having no access to a floor plan or previously constructed SLAM map. Eventually navigate to the point that it has gathered enough information to ask the question, and then decide to actually stop and answer it. So this is a challenging task. It involves perception for the agent to understand where it's going and to answer the question. There's natural language processing to know what it's even trying to do. And there's long-scale reasoning and planning. It's a good test bed for a lot of the things we want to try to do. We build this on top of the SunCG environment, or SunCG dataset. It's a collection of 45,000 homes. They're synthetic, so the perceptual realism is a little low. But the semantic realism is very high because humans have actually produced these. They're crowdsourced environments. And we glue these together with some fabulous work from some colleagues at Facebook AI Research, House 3D, a simulator that gives faster than real-time navigation through these environments, along with semantic labels and depth. And it does basic collision checking. OK, so we decide to start small and not ask super complicated questions. We make use of a subset of the environments, objects, and room types. And we ask questions about objects' location, color, and relative position. So we're starting small. And we train an agent that is a hierarchical planar controller module. So in a nutshell, this is an end-to-end agent that goes from egocentric images, so raw pixels, and the question words, all the way to navigation actions, and finally question answering. So it's an end-to-end system that does this task. We separate it into two levels of control, where there's a planner module that makes higher level sort of intentions, like go down the hall, and a lower level controller that takes care of actually executing those before returning control. So let's see what this might look like. On the top left, there is a question, what color is the fish tank? And the model is spawned at this location. It navigates the environment entirely from first-person vision, finds a fish tank, and answers the question blue. On the right, we have what room is the candle in? Again, the agent is spawned at a random location and has to navigate. Turns around for a little while, can't seem to find a candle, spots it in the dining room, gets close, and then identifies that it's a dining room. And this is all, again, in novel environments from egocentric views alone. And part of the excitement that I have about being given this opportunity to talk to you all is this isn't a single point. There's been a tremendous amount of work in this area just within the last year. So everything I'm going to show in this slide is about 1 year old. There's these environments, ranging from synthetic ones like Sun CG I showed you earlier, all the way to rich 3D scans of real people's homes that have been annotated. There's been a huge suite of simulators with more on the way that add capabilities, including not just sort of collision detection, but also sound emulation. So if you want your agent to have auditory suites, you can incorporate that into whatever task you design. And there's also been a great number of tasks that also leverage perception, language, and planning. So there's a great deal of work, and we're approaching a place where it might be believable that we have this simulation-based pre-training. So before I ever get to a physical robot, I have a brain in a box. But the challenge is, how do I generalize to real agents? And that's the call I'm sort of leaving to all of you today, is how do we cross this gap? And I'm excited to see the transfer learning, domain adaptation, and more realistic environments that come out in the next few years, thanks to all your efforts. Thank you.
And now, please welcome our final DARPA Riser presenter, Emily Graczyk.
Good morning. My name is Emily Graczyk. I'm a research associate at Case Western Reserve University, and I'm honored to have the opportunity to present to you today my ideas on how we can use electrical activation of the nervous system to investigate and augment sensory perception. We work with people who have lost a hand due to a traumatic injury. When someone loses a hand, they lose both the functional and the sensory capabilities of the hand. Fortunately, there are several prosthetic options available to people that restore grasp function and the ability to manipulate objects. These sorts of prostheses are typically controlled by contractions in the muscles above the level of injury, which then drive prosthetic motors. However, there are currently no commercially available prostheses that provide sensory feedback to the user, and this is a critical need for wounded warriors. Sensation helps us grasp and manipulate objects. It gives us information about what we're touching so that we can handle it appropriately. Sensation is also key for our psychosocial connection to those around us. You can imagine a wounded warrior returning home from war with an amputation and wanting to pick up their newborn child for the first time, and how hard this might be if they don't have that sensory feedback. To meet this need, our group uses peripheral nerve stimulation to restore the sense of touch. We do this by implanting electrodes around the nerves above the level of injury, and then using electrical stimulation to activate the nervous system. In the attacked sensory system, when your hand comes in contact with an object, there are receptors in your skin that pick up that information and send it up your peripheral nerves. This information is encoded through complex neural firing patterns, and then hundreds of these neural firing patterns come together in the brain to create a holistic sensory percept. When someone loses their hand due to an amputation, the nerves above the level of injury are still present, and we can then interface with these nerves using electrode technology. When we provide electrical stimulation to the nervous system, this is then converted into a neural signal, which then is sent up the existing sensory pathways to the brain and perceived to be a touch sensation. Through the haptics program in the Biological Technologies Office, we've demonstrated a great deal of success in restoring sensation to persons with upper limb loss. Although these persons no longer have a hand, the electrical stimulation enables them to feel sensations on their missing hand and fingertips. And these sensations are relatively small and in functionally relevant regions of the hand. We're also working to integrate this sensory information with control of advanced prosthetic technology. In this video I'm about to show you, a participant is using a decahand, which was actually developed through a prior DARPA program, to find an object in an opaque bag. Typically, without vision and without sensation, this task would be almost impossible for a prosthesis user. But with sensory feedback, he's able to tell when he's made contact with that object and when he has grafted appropriately to remove it from the bag. This is an example of how sensory information provided through electrical stimulation can improve prosthesis functionality. Electrical stimulation also gives us a new tool to study the nervous system and understand neural coding. We've used this previously in the lab to investigate the perceived intensity or magnitude of artificial touch. We do this by leveraging an understanding of basic neuroscience. Neurons typically communicate to one another through what's called an action potential, but you can think of that as just being a binary 1 or a 0, or in this plot, a dash or the lack of a dash. We can activate one neuron with electrical stimulation or multiple neurons at the same time, and then we can activate them repeatedly over time through stimulation pulse trains. We then use clinical tests in the laboratory with our participants to assess how that sensation feels to them. In this case, we assess the perceived intensity. We then combine this experimental approach with computational models to understand neural coding. We found that if we increase the number of active neurons, which would look like this, or we increase the activation frequency of our population of neurons, like this, both have equivalent effects on perceived intensity. This tells us that both of these neural features are critical for perceived intensity and elucidates this neural coding mechanism. What this means for the wounded warrior using a sensory prosthesis, though, is that we're able to provide fine gradations and touch feedback, which will enable them to precisely control the amount of pressure they're exerting on an object so they can handle it appropriately. I propose that the next step towards providing optimal artificial sensation for wounded warriors is to investigate complex perceptions. One type of such perception is sensation quality, such as a texture or an environmental stimuli. This type of information would broaden the type of tasks that an amputee would be able to perform with their prosthesis and give them a more natural experience. Another key type of complex percept is emotional or affective touch. This sort of information could improve social interactions and could perhaps enable people to feel as if they have a real hand again. What's exciting is that we actually have preliminary evidence that both of these types of complex percepts are achievable with artificial sensation. This plot here demonstrates the output of a computational model which predicts stimulation patterns that enable us to evoke neural activity that very closely mimics neural activity in the attack nervous system. And preliminary tests with our participants demonstrate that these sort of patterns can be perceived to be more natural. We also know that artificial sensation can have a psychological impact on prosthesis users. In this video, our participant discusses using his sensorized prosthesis at home to interact with his loved ones for the first time since his injury.
Sensation on, I feel that I'm actually touching my daughter's hand, not the prosthetic, and becomes natural to them, just like it does to me. It makes a big difference.
With electrical activation of the nervous system, we can investigate neural coding and understand how to convey optimal touch feedback. And we can also provide functional and psychological benefits to wounded warriors, enabling a new frontier in human connectedness. Thank you.